Thanks very much, everyone. Thanks very much for coming along. I'm Lisa Crossman. I have a PhD in microbiology in the lab, and I have a consultancy firm doing freelance bioinformatics on the Norwich Research Park. And yes, so these people along the bottom have given me money in the past, which is good of them. Okay, so back in 2020, 2021, I was really excited to find this actual plot saying that by 2030, synthetic data will completely overshadow real data in AI models. And I thought that was absolutely mind-blowing. I thought, what is this synthetic data going to be doing? So what did they mean by synthetic data? Well, they meant artificially generated data, either from simple rules or statistical models and simulations and other techniques, as opposed to real data obtained from direct measurements, which is, of course, constrained by cost and logistics and privacy reasons. So this really seemed to speak to my area of DNA sequencing and health, because collecting real data seems to be getting harder and harder as we go along. Just finding the people, getting their consent and everything is quite tricky. So what is synthetic data? Why is it important? And we're going to look at some specific examples. So mainly in terms of its uses, we've got the data privacy aspect, which is really important. And another good point about it is that it's really good for testing and simulation and teaching and learning, because you can just go ahead and give somebody a bunch of data. There's no problem. They don't have to sign MTAs or NDAs and so on. And it could be really good for enhancing machine learning models in terms of balancing classes. And a lot of the time, the data that we have, you might have like a lot of negative or healthy samples and only a few positive or unhealthy samples. And therefore, you want to balance those classes out to do your machine learning. So the synthetic data could help with that. And we do have some other synthetic things. You're probably wearing synthetic clothes, for example, and other synthetic things are like diamonds. So natural diamond is made of carbon. It's created over 1 to 3 billion years ago, 85 miles below the surface, under very high temperature and pressure. And it's really difficult for us to get those diamonds out. But of course, we've got synthetic diamonds as well, such as cubic zirconia and lab-grown diamonds, and they both have diamond optical properties. So it's really hard to tell the difference, and you probably need an expert to tell the difference. So in terms of synthetic versus real data then, in terms of the scale, with the synthetic data, you can have unlimited data sets or limited by your compute processing, whereas the real data is going to be limited by its availability and how you can collect it and cost. In terms of privacy, you can build that into your synthetic data so you can have enhanced compliance, whereas there's always a potential risk on the real data side of it leaking. So with diversity and bias, you can build in your fairness into your synthetic data model, whereas your real data might lack some variety or be biased in terms of coverage and may not have all your edge cases. In terms of speed, you can just do it on demand, whereas your real data requires more than approvals, really. You probably have to collect it. You have to find some samples. You might have to have patients. You might have to do lab work. It could take a long time. But with the quality of synthetic data, you know that you need to reflect the real-world pattern. Real data still may have biases. And types of synthetic data then. So you probably see the iceberg story before. Structured data is around 20% of all the data, and that's the data which is collected in databases and has tags and is well understood, whereas unstructured data is everything else. And of course, there's big data as well. So Facebook generating about 4 petabytes of data a day. Instagram, a bit more than that, 70 million posts a day. YouTube, 720,000 hours of video a day. WhatsApp, about 2.1 million terabytes a day. About 65% of individuals use cloud storage as their main storage. The percentage of unstructured data, 80% of all data. It's been estimated only 12% of data collected is ever analysed and used. And the current world data volume is estimated at 141 zettabytes, whereas back in 2005 it was about 75 terabytes. I nearly have that, in my house. And people are generating 402 quintillion bytes of data a day. But if you can't get your head around it, that's because you can only store 2.5 petabytes in your head. So there's various subject areas with interest in synthetic data. So we're talking about telecommunication, manufacturing, e-commerce, social media, automotive, banking and finance, agriculture, and healthcare, which is the agriculture and the healthcare part, which is where I'm most interested in. So synthetic data uses in the biosciences, it's something that's just really starting to bubble up now. And was really one big plus point is that you can use it for private data that can't be shared for analysis. So health data in particular. And to provide a more balanced data set. Another possible area is inventing new genes of a particular type. So possibly something like improving washing powder enzymes or something like that. Can it tell us more about evolution or protein structure? But of course, at the back of everyone's mind is still some concerns. How can we know if the data set that someone's given you is real or synthetic? Could there be some kind of malicious intent? Is it just a reflection of the training set? You could be missing out on some important edge cases. So back a few years ago, NVIDIA proposed some differential privacy, as in privacy-preserving AI in healthcare. And what they proposing was that various hospitals or research centres could do some medical imaging, and that these images would then be used to train a local model. Then all you need to do to share that data is actually just share the weights from the AI model and into a global model, and then you can just keep going, downloading and uploading and improving the model. So this is part of differential privacy, which is mainly about adding noise to the data so that it can become private. So differential privacy then is defined as a mathematical framework to protect privacy while sharing statistical information. And it builds into it a way to measure if the data is private enough. But synthetic data is not inherently private, so you still have to build privacy into it. And there's obviously a trade-off between the privacy and the utility of the data, whereas when it's completely private, it might have no utility, whereas on the other side, maximum utility might not be very private. So interestingly, in the early days of COVID, I'm sorry to mention it, but it helps everyone to understand what I'm talking about. So in the early days of COVID, they were doing some imaging. They were doing X-ray images to find out if somebody's disease was going to progress. And they had taking a lot of images, but it was difficult to get enough radiographers to look at them and discover if the person was actually going to have disease progression or not. And so they turned to AI. But there were only really about 100 quality images. And it was very difficult with privacy. People didn't really want to put their data up there. And there was another problem with positive and negative ratios. There were a lot more negatives than positives. And they also discovered that not only did they want to look at healthy and COVID, but they should be looking at healthy COVID and pneumonia. And then it was found that the AI was actually cheating, because although they trained it and it seemed to have good accuracy, it was fixating on some specific areas where the hospitals had put tags and notes into the X-ray image, and the AI was just fixating on those. So that is why synthetic data really came in on the medical imaging. And there was a couple of papers where people used huge synthetic data sets, deep learning based approaches on X-ray pictures. So where I come into it then is really that I'm interested in DNA, which is of course the molecule of life. And this is a reconstruction of the double helix model of DNA, which uses some of the original metal plates that James Watson put together in the 1950s. And you can find this here in London in the Science Museum. And DNA itself is a phosphate sugar backbone, which is made up of 4 bases as well. And they're adenine, thymine, cytosine, and guanine. And we abbreviate those to A, T, C, and G. And all of the DNA sequence in an organism is its genome. So DNA is actually really big data as well. And what we have is that all the DNA sequence that we've currently got in the world is uploaded and is shared to the International Nucleotide Sequence databases. And they are located in Maryland, USA, and EMBL, which is the EBI in Cambridge, and the DDBJ in Japan. And I was at the EBI in December, and they said they were storing about 200 petabytes on site, which is all the DNA sequence which is publicly available, and all of it again as a backup. And so they're actually looking for some more collaborators. And they're hoping that they could kind of have a model where different countries keep their own data on their own soil, as well as having this massive database as well. So what does DNA sequence look like in terms of data? Well, it's actually just text data. So at the top part there, you can see the short read data, which comes from the Illumina company, and they have about 80% market share. And so the top part is the actual sequence. And then after a plus sign, you get the quality score. And as it's more towards the front of the alphabet, then it's a better quality. And as you can see, it drops off towards the end of the sequence read. But we also have long read data, such as that from the Oxford nanopore technology. And you can see this on the bottom. And this is actually, it's a squiggle plot, they call it. And this occurs when the DNA goes through the nanopore itself and is measured as a current change. And then they have a deep learning model which calls the actual bases in groups. So you might think, well, I'm not doing anything with DNA. Who cares about DNA? But actually, people have thought of using it to store data long term. So there's a French company called Biomemory. They've come up with a credit card sized data storage solution. And for €1,000, you can store 1 KB for 150 years. For your €1,000, you'll get 2 of these cards and a voucher to sequence the DNA. And once you've actually sequenced it, then it will be destroyed. So that's why you have to have 2 cards. And they estimate that about 70% of data is cold stored. and archived, and that's why they feel that it could be a good option for some people. So I'm quite interested in the idea of computationally engineered biological sequences, which seems a bit of a mouthful, but I'm trying to describe what I mean to people. So people often call some sequences artificial sequences in molecular biology, and they're talking about cloning physical sequences. So they're chopping bits of DNA and adding them to other bits of DNA. So I'm not talking about that. And there's also, people call them synthetic sequences by printing custom sequences. So that's where you actually kind of artificially add each base to another one. So you can decide your sequence in advance. And you can't usually print that many in a row, and it soon gets quite expensive. But people call them synthetic sequences, but they're also physical sequences, so I'm not talking about those. And you can also do random sampling of longer sequences with bioinformatics. So I'm not talking about those either, although they could have they could be interesting. So I'm talking about machine learning produced sequences. And we have to remember there's still rules, even if you're to go on and produce these sequences. Most of them should start, for example, with ATG. And I thought, well, maybe ChatGPT can already do this, because it can do lots of other things. So I asked it to tell me a DNA sequence of E. coli antibiotic resistance gene. And it knew a bit about it, so it's done all right. But then it just made up some sequence. So yeah, it's not quite there yet. So there are some frameworks currently that could be used for computationally engineered biological sequences, and one of those is AlphaFold 2 from Google DeepMind, which is for protein structure. And they've encoded their sequences as protein sequences in this multiple sequence alignment format. And as you can see, when you line up all the proteins from different organisms, they're the same protein in each organism that has to be lined up. And you can see in the blue blocks that some of them are conserved across all those proteins, and therefore it's not a big jump to imagine that those could be important. They might be important in terms of the structure, or important in terms of the function. So that's one way of encoding them. But it's not always perfect, because sometimes we don't have that many examples of a particular protein, and some proteins have got variable lengths, so it's very difficult to know how to line them up. So there's another thing which I've found recently called Grover, which does DNA sequence embedding, and that uses small pieces of DNA. And of course, we just talked about this before, the Oxford Nanopore base sequence calling, and they were calling 6mers of that squiggle plot. So those are k-mers. And what are k-mers? Well, k-mers are overlapping windows of DNA sequence. So you've got here a DNA sequence, and you step one across each time. And these are 7mers, so you've only got 7 in each of those. And if you did that with a word, you could imagine stepping through the word. And then this is how we do our assembly. So we use a graph-like procedure. And you can see there's a bit of a tricky problem if you've got a repeat. So what if you wanted to generate synthetic data with Rust? Well, I found a few crates. There's Rig, which does synthetic data powered by LLM, so it calls to ChatGPT. There's Fake-It, which is this one. It's faking some beers, and some of them are quite strong. And there's Synthetic Data Showcase, which has Python bindings, but it's also written in Rust. And there's LACE, which is Bayesian non-parametric tabular synthetic data. So why Rust? Obviously, what's it got to do with Rust? Because, a lot of these machine learning models are written in Python, so why would Rust have anything to do with it? Well, I originally got interested in Rust after somebody asked me to do some bioinformatics work that was supposed to be really fast. And I thought, well, I'm trying to do it in Python and R, and everybody knows that Python and R are not very fast. So I thought, I was looking around at different computer languages, and I came across the computer language benchmark games, and I noticed that 4 of those games or tests were relating to bioinformatics directly. So there's match DNA k-mers, substitute magic patterns, generate and write random DNA sequence, hash table update and k-nucleotide strings, read your DNA sequences and write their reverse complement. And they also provided a handy table, which includes the energy, time, and memory across those different languages. And as you can see, the traditional languages of bioinformatics are at the bottom, very much at the bottom of the table, whereas Rust, very much near the top. And so it looked like a really good option. So I wrote some scripts in BioPython, which is obviously the bioinformatics Python library, and in Rust. And I've been doing BioPython for many years longer than Rust. So although I wrote these scripts, and I'm sure that other people could make them more fast and more efficient, then you'd expect me to be better at writing the Python one than the Rust one. And I didn't really try to reduce the number of lines there either. And you can see that the Rust one was hugely much faster. So then it turned out that if you were to convert this text file type, which is a way that we store some of our sequence data, so this actually contains the sequence data itself and details about the proteins. Now, if you were going to convert this type to just the DNA sequence on its own, then in Rust, if you did it on 10,000 different files, in Rust it would take you 25 minutes, but in Python it would take you 4 hours if you do them on a single thread. And that's obviously you're not going to do it on a single thread, but the resource that you're going to be using is so much more. So I put these into a crate, which I've called MicroBioRust, and we do have Rust Bio, but I feel that microbial genomics has different requirements to human genomics and work on plants and so on. And that's because we have a lot of very small files, whereas they're working on like one very big and complicated file. And we're also trying to step across the divide from bioinformatics and Rust developers, and we're trying to step across the divide further into biologists as well. So I felt that we could probably use a MicroBioRust. So I started off by writing a parser that isn't in Rust Bio for a particular format that we have that's common. And this is the Genbank format, which is the way people store DNA sequence in the US sequence databases. So the Genbank format looks like this. You have a records, which is like at the top level, and each records might have one or several record, and each record may have none or several features. So I worked out to use an enum for these attributes. So the source attributes applies to the records, and the feature and sequence attributes apply to the features. And so if you look at this, then the source attributes have got things like the start and stop of the top level amount DNA sequence and the organism that it relates to, things like that. And then the features, where they're talking about the DNA gene sequence and its protein translation and which strand it's on, because it can be facing that way or that way, plus or minus. Its start on the record, and so on. So what I did was I realized that we had these enums, and I was going to have to write the same function again and again to set and get these particular fields. So the start of the gene or the stop of the gene, the organism, talking the strain. So if it's like E. coli, it might be K12 or it might be HS or something like that. And so rather than like keep writing the same function, get this, set that, I was looking into macros. So created some generation of the getters and the setters for getting the sequences and so on. So this is one macro in the end, and had some help from Christopher and Pranith on the open source. So yeah, if anyone wants to come along and do some help, you might think that's rubbish, but you've done it all wrong, but that's fine. Just come and tell me about it. And yeah, it would be great if anyone wants to join in. So going back to synthetic data then, working with this group, the Elixir Machine Learning Focus Group, and have come up with some recommendations for looking at synthetic data and other data types and describing them. So what we want is that the data size and distribution must be representative. We need to have independent train and test sets, and we'd like data to be released with the exact splits. Then in terms of optimization, we're looking at evaluation sets not being used for feature selection or parameter tuning. We're looking at hoping to get metrics that show no over or underfitting, and to explain model validation techniques, describing the model in terms of whether it's a black box or interpretable, and reporting on the execution time. Evaluation, we're looking at comparing it with public models, if there are other ones available, and trying to adopt community benchmarks so you can evaluate the whole thing on a final independent data set and try to gauge the robustness. And so Elixir is a group of research institutes across Europe, and they have sets of focus groups. So this is one of the focus groups. So set out to produce some synthetic data in Rust, and I was quite intrigued about producing some protein sequence. So I actually first of all wrote it in Python in like 2020, and then so I converted it to Rust subsequently. And basically the idea was to encode the sequence just as a character encoding, and then embed that. So this is basically a Rust bio script to get the sequence out of the format that it's in, which is just one protein after another with a greater than sign. And I decided that it was much more efficient than the Python script if I did all the pre-processing in Rust and then handed over to the Python script. It's still the Python script, but wrapped in Py03. So that seems to have worked quite efficiently. So in terms of the actual neural network, it's a TensorFlow, and it is not a transformer, but it seems to work better than the transformers that I've tried for the character network anyway. So so this is just building a module, a Pi module from the code, and it just runs the training and got some good results. So I tried it on 2 different data sets, and one is the spike protein from COVID, which is the one that was targeted by the vaccine. And there's also the influenza hemagglutinin, which is a separate training run I did, and that is the one that's targeted for the flu vaccine. These are all the different amino acids. So if you are looking to see if their composition is the same, then you'd expect the 2 boxes to be in the same place. And they're not too far off. But I think the spike protein was better. So that worked better. And I think it's because the spike protein is actually better conserved than the flu, the hemagglutinin. So that was interesting anyway. So if you're looking at the distribution of the data that I got out, so looking at about 1,000 of the sequences that are produced, then if you use a random seed from the data set, you actually get quite a lot of MERS, and MERS is a protein, spike protein. MERS is similar to SARS-CoV, which is the virus causing COVID, but it's actually from camels, and the original data set was quite MERS heavy because I downloaded it in 2020 before everyone put all the COVID sequences in it. So if you use a seed for the SARS, so this is like a prompt, so just using the very beginning of the protein, you can see that we get a lot more of COVID sequences, and some also came from the bat SARS-like protein, which everyone thought that COVID had come from bats. But sometimes it gets confused and just wanders off and does a bit of MERS. So we definitely need metrics for synthetic data sets, and we need to be measuring the accuracy. We really need to know if the data size and the distribution is going to be representative. They have to have similar key statistics. We need to cover all our edge cases. We're probably going to need some type of application-specific evaluation, and maybe also an expert evaluation. And we've got to consider the fidelity and privacy trade-off, and we might need a privacy expert as well, especially for human data. So something else which is interesting in terms of synthetic data was digital twins. And the digital twin concept comes from engineering and industrial. It's also been used in supply chains, process design, weather and farm management. And people are thinking, could we create synthetic patients for precision medicine? So like instead of doing clinical trials with animals and human volunteers, could we make like a whole person as a digital twin and test that with clinical trials instead, which would be so much cheaper. And, you know, we could try out a lot more drugs that don't make it. So that would be excellent. So when would we want to go synthetic then? Where privacy is a concern, if you have unbalanced classes, if you want to meet data production on demand, and when your metrics are good. So will synthetic data make data bigger or smaller? Well, it depends. It's going to be bigger if you're adding data points, but more probably smaller if you're going to be creating clear balanced groups, because you're not going to have loads of one type, but it might depend on the data complexity. So some facts up to the minute. This month, somebody has produced an AI that can predict coronary heart disease, and that uses SMOTE, which is synthetic minority class oversampling technique. And a company called Capgemini announced they're making synthetic protein sequences, and they've, I think you'd have to get the get the magnifying glass out to see that one, but they have improved on an enzyme which can degrade plastics. So that sounds really good. And they've also improved a protein that's used a lot in research to do microscopy and markers, green fluorescent proteins, so they've made that brighter. So it sounds like, this kind of field could be coming along, and we'll be obviously needing to build a lot of benchmark data sets. And at lunchtime, I read that there's a new AI called Evo2, which is also making synthetic protein sequences. I'm not, they haven't released a lot of details about it apart from kind of a lot of yay. So coming now near the end, so what do you think all these pictures have in common? So we've got Mary Poppins' magic bag, the Lion, the Witch and the Wardrobe's wardrobe, Oscar the Grouch's garbage can, Hermione Granger's magic bag, the TARDIS, and black hole. Any ideas?
Hologram inside?
Yeah. So I was wondering if it was possible to reproduce our data sets with Gen AI for storage. So could we make it smaller by having a model and just like cramming all our data in, and then instead of actually keeping our data, just producing it on demand out of this model? But there are a few problems with that, because current models are designed to generalize and not memorize. But you might be able to get around it a bit if you have the exact metadata. You could do some prompt tuning. And it's partly due to past deliberate design choices to avoid things like GDPR, copyright, and ethical guidelines. So I think you'd have to change some of the ways models are made if we wanted to do that. But my flu model, this was the data, and the model itself was about 1.7 times smaller. So it's kind of interesting. I like the idea of it. So in terms of future trends, it looks definitely like synthetic data's on the up. We're about halfway through this. We'll see what happens in another 5 years. So we talked about synthetic data, its uses and types. We talked about it in genomics. Talked about microbiome Rust, and if anyone wants to get involved with that, it'd be great. Synthetic data with Rust. We need to be careful with our metrics and the future of synthetic data. So I'd definitely like to thank the Elixir Machine Learning Group and Genevieve from Bingham University and the Women in Rust and Shuttle team for doing really excellent Christmas coding challenges. Thanks very much.
Any questions?
You said that you're kind of, looking forward in the next 5 years to see how this technology develops. Do you have any predictions yourself about where it will go and how it will be used?
Well, I think that at the moment, everyone's just kind of feeling their way. But I do think in terms of the imaging, that's probably going to be the first thing that's going to come to the fore. But it's essentially a bit of trust about it. Are people going to trust, their cancer image to an AI to look at? It's been suggested before that you could have one human and an AI, and if they both agree, then that's all right. Or if they don't agree, bring in another human. So that would be one way of kind of breaking people into it gradually. In terms of doing like synthetic proteins, I think that may be a bit further away, and really looking at trying to get a really good use case. So at the moment, this Evo2, it sounds like they haven't really got a massive use case, but maybe they're hiding it. And in terms of the storage, it's further away again, but yeah, kind of intriguing.
Very interesting presentation, thank you. I suppose one of the things about synthetic data is that the more of the synthetic data you have, are you not worried? I mean, a lot of people are already concerned about the collapse of models because the models are constantly being retrained on synthetic data. So, of course, over time, I suppose that dilutes the information pool, which is, I suppose, really important to you guys. And eventually, so I suppose in bioinformatics, would you be concerned about that your models are no longer, how was best to say it, they no longer produce anything interesting, they just produce the same things over and over again?
Yeah. So I suppose that's in a kind of way, it's a bit of overfitting if you're doing that. So yeah, I think that's something that definitely need to consider. And I think there's a tendency for the generalization always coming from ML models. And so it's those edge cases which are going to be so important. So I suppose you could kind of split it and keep the edge cases separate and have the generalized data set going around a few times more, maybe.
So you talked about data bias in our work, with digital twins, and you have a lot of demographic information that you can have, but then you have things that you might not consider. For example, one problem that we have is that we're getting all of this data from the UK Biobank, but then the people that the data tend to be for people that are very health conscious. So we're having like healthy patients, but you are like healthier than the average person, let's say. So there's always bias, but there are things that we cannot, that we don't, that are very subtle, that can influence a lot. So I don't know how we would solve that problem, but I don't know if that's something that I guess in DNA is not a problem, but it's like you can have representative data, but it's not really representative because of all these things that we don't measure.
Yeah, and I guess the problem is it's really hard to know if it is actually representative, because you could be losing a whole group of people who weren't ever interested in health or something. And then they could be the people who are eating the worst, and they might have some different characteristics entirely, like if you're studying gut microbiome or something like that. So I suppose perhaps the only way to get around that is to try to gather data in different ways or in different situations. So maybe when people come to the doctor for something else, or ask for consent there, or compared to sort of going out, because I work a lot with the Quadrum Institute in Norwich, and they ask for volunteers to come in and eat various special diets and things like that. Those people are, quite likely to be biased towards your healthy set. So maybe just trying to gather data from different environments in a way might help. But it's always going to be an issue, I guess.
So the synthetic data and real data, as you say, synthetic data will be quite lot more in 2030. How confident the analysis will be? How will the people feel that whatever the analysis the model is giving you is real? And this is bioinformatics field and things like that. So, how will we feel confident that what we're doing with that analysis is right? And is there a scope of the hybrid model where you could do the analysis on real data and synthesis data and verify that whatever the analysis you did on synthesis data is sort of backed up by the real data sort of analysis as well?
Yeah. I mean, that sounds, quite sensible, having some type of hybrid check. I mean, you definitely have to make sure that in your data set, it's very representative of the real data, in terms of if you're using it in that kind of a way. If you're using it to train a model and you're wanting to create balanced classes, then that's slightly different, I guess, in terms of looking at the distribution, because you wouldn't want to necessarily, in that case, mirror the distribution of the real data, because that might be very, very biased towards, if we were looking at a rare case of a genetic disorder or something, then, there would be very few of those examples. So you want to put in like 50-50 split or something like that. So maybe it's got more hope for that kind of thing, the avoiding unbalanced classes coming online sooner than measuring the whole distribution, maybe. But I think that you'd have to keep the real data and kind of keep comparing it or something, so that you know what's going on.
Any more questions? Thank you, Lisa.
Thank